Well, I'm the only other person here, so yes.
Well, it's only 14 though. They have 4 minutes.
I think we only had 2 or 3 people last time.
Yeah, I've watched all the recordings so far, and like I have notes on the math part of it, but I don't know if we could. And I know the answers are all at the bottom too. I understand that, but if we could just take a couple and go from there, I'd appreciate it.
Yeah. I'm not sure which worksheet you're talking about.
Let's actually do the mole worksheet number 3.
Okay.
For starters. So I will need the periodic table, correct?
For sure.
Am I like screaming at you because
You're not.
I can like quiet down a little? Okay.
You're fine.
So I have my periodic table ready and my calculator.
Okay. Which one do you want to do? Which one would you like to do?
We do number 1 and work our way through it, because if we do this one, won't that help answer like all the other worksheets?
I totally agree. Yes. For sure.
What's that?
Yes.
Okay.
So when we're calculating molar mass, what we're trying to figure out is how many grams are going to be in a single mole of whatever we're looking at. So in this case, we're looking at NutraSweet, and it has that chemical formula. So 14 carbons, 18 hydrogens, 2 nitrogens, and 5 oxygens. So we look on the periodic table, and if we look on the table, we'll see that the carbons have a mass of 12.011, and the hydrogens have a mass of 1.00795. If your numbers aren't exactly what mine are, that's totally fine.
Yeah, that's what I was just going to.
Your number probably says 12.0.
With 2 decimal points.
That's fine. Doesn't matter.
Okay.
And then these are just the numbers I know off the top of my head. So 14.0067 and 15.9997. So there are 14.
Would hydrogen be then 1.01?
Sure. So there's 14 carbons, so I'm going to have to multiply that 12 number by 14. I'm going to have to multiply the the hydrogen number by 18, the nitrogen number by 2, and the oxygen number by 5, and then add all of those things up.
Then you times them all.
You see where that number is coming from, right?
I do so far, yes. Okay, so you multiply all those. You're going to give me a minute to do that?
No.
No, okay, moving on then.
So what does that 294.43 number mean to you?
And then add.
Yeah. What does that 294 number mean to you?
That is the atomic mass.
No, it's not.
Of all of them.
No. Not with that unit.
Well, I know that the mole is the 6. Okay, because the mole is the 6.02 pounds.
10 to the 23rd, yes. But I lost you. I can't hear you anymore. I can't hear you. Okay, so do you see this ABC divided by B and D? Mathematically, what would you do here? You cross off the B's, right? B divided by B is equal to 1, so it's gone. So do you see this gram over here? That gram right there? I need to get that gram to cancel out. So how am I going to do that? I need to gram in the numerator. So, which is great because in my question, it says I have 10 grams. So I'm going to write 10 grams of aspartame here. And what that does for me is allows me numerator, denominator, those guys cancel out. So what unit hasn't been canceled out? Moles. All the other units are gone. So then I just take 10, because it's in the numerator, so I'll type 10, and divided by 294.43, and I get, my answer here is 0.034. So like 3.4% of a mole, a very small amount relative to the size of a mole. Okay, so now it says calculate the mass in grams if I have 1.56 moles of aspartame. Okay, so let's, I'm gonna delete. I don't want to let me select this. Oh, don't do that. All right, I'll just erase it. Okay, so in this question, I want to know how many, I want to know the mass. So that means I need to know grams. So this time I'm going to write 294.43 grams divided by moles, because what I'm looking for in the end here is my answers needs to have grams in it. So I put the gram in the numerator. So now what I need to do is I need to cancel out that moles. Well, that's fine because in the problem it gave me 1.56 moles. So moles in the numerator, moles in the denominator. I don't have anything else to do here except multiply them out. So the 294 times 1.56. And I got 459.31 grams. So that makes sense to me because 1 mole has a mass of 294, and this is more than 1.5 moles. So it shouldn't be close to 600 because close to 600 would be 2 moles. I'm only at 1.5 moles, so 460 seems reasonable. You okay with that? All right. Let's erase this. And let's do, how many molecules are in 5 milligrams of aspartame? All right, this is kind of a silly question, but that's fine. So I need to know how many molecules, and the way I get molecules is by going through moles. So I'm going to type it up, I'm going to write it upside down again. So 1 mole of aspartame is 294.43 grams of aspartame. I need to cancel the gram unit out, and I didn't get grams this time, I got milligrams, but that's okay. So what I'm going to do is write 5 milligrams. Now I can't cancel milligrams and grams out because they're not the same unit, but I do know a unit conversion to go that's 1,000 milligrams is equal to 1 gram. So do you see what we just did there? How that helps us mathematically? I have a milligram in the numerator and one in the denominator, and a gram in the numerator and a gram in the denominator. So I got rid of all my mass stuff. I still haven't answered my question yet, which is about molecules, but that's fine. So to cancel out this mole unit over here, I'm going to write 1 mole down here, and then I'm going to write 6.02 times 10 to the 23rd, because that's what a mole is equal to. And so now the moles are, in this case, molecules. If I could spell molecule. All right. So this is going to be a really big number. So I've got 6.02 E23 times 5 divided by 1,000, and then divided by 294.43, and I get 1.02 times 10 to the 19th molecules. Great. Okay. A giant number, and that makes sense because they're really small, so even 5 milligrams would be a lot of them. Okay, so the next question is, I don't know, slightly more interesting. It makes us think about what the molecule is composed of. So this is asking about atoms of nitrogen. Okay, so what that means is I'm looking for a number. So the only way I can get to a number is by starting off with moles. So I'll write it upside down again. So I've got 1 mole, and then I've got 294.43 grams. And this is aspartame. And so it says we've got 1.2 grams of aspartame. Or this is not aspartame. I'm sorry, I keep saying that. This is aspartame. I got my wrong synthetic sweetener. So 1.2 grams of aspartame. So this allows me to cancel out the grams. That's awesome. So I should probably have been writing aspartame here this whole time. So if I have 1 mole of aspartame, oops. How many moles of nitrogen do I have? So this question, the analogy for this question is, if you had 1 bicycle, how many tires would you have? Great. If you had 1 dozen bicycles, how many dozen tires would you have? No, dozen tires. No. 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 How many, not how many tires, how many dozen tires? So you kept trying to put up 24. So what should you have been putting up? I don't know. No, not 12. No. 2. Right? If you have 1 dozen bicycles, how many dozen tires do you have? 2. Okay, so you can figure that out really easy because it's the math isn't hard. So if you had 1 dozen bicycles, how many actual tires are you going to have? 24, right? So how many dozen is that? 2. Okay, so it's easy to see it that way because we can visualize 24 things, but we can't with moles of atoms because the number is astronomically large. So where do I figure out what this number is? What number is going to go right here? How do I figure that out? I go up to my chemical equation. You're right, and the answer is 2. You're right. Every single time I have one of these molecules, I've got 2 nitrogens. So a 2 goes right there. And then this asks how many atoms. Okay, so then I can go 1 mole of nitrogen is 6.02 times 10 to the 23rd atoms of nitrogen. And so let's see, what do we get here? 1.2 times 2 times 6.02 E23 divided by 294.43. That's it. So it looks like I've got 4.91 times 10 to the 21st atoms of nitrogen. This is really just about you being able to manipulate the units. And this might seem what I get with this is, why in the hell would I ever have to do this? I'm not going to be a chemist. I'm not going to be a physicist. I'm not going to be doing any of this kind of stuff. All we're doing here is manipulating units. And if I'm not mistaken, you're looking at getting into the nursing program, right? Oh, you're not? Okay. Well, most of the people who are in this class are trying to get into the nursing program. And the issue with the nursing program is you have to manipulate units all the time because the medication is going to be in one kind of dose, but the doctor ordered it in different units, and it was given in kilograms, and you got the person's weight in pounds. So there's just a lot of unit manipulation that you need to do. Um, and it's actually, oh, will something like this be on the test? No, not really. But our goal is to cancel units out. All the units we want canceled out except for the one we want. So in this case, we wanted atoms of nitrogen. So we kept having to cancel stuff out until the only unit that was left was atoms of nitrogen. I should have canceled that, right? Canceled that. And then all those units are gone with the exception of this one. And that's how it works. I use this method to do all of my math problems. I never have to memorize any formulas, ever. I don't even bother with formulas because I just use this for everything since my junior year of high school. um, not a lot of unit calculations. Yeah, I don't know. Last time I took stats was a long time ago, but I don't remember doing any actual math. It's like throwing stuff in Excel and coming up with histograms and things like that. Okay. All right, we can do this next one about the mass we have in this number of molecules. Uh, so we're looking for mass. So I'm going to just go ahead and start with 294.43 per mole. So the way I forced this process to work for me is twofold. One, I know what I'm trying to do because I look at the question and I see this word and I know I need a mass unit like grams. And so what I do is um, I put the first thing that I put in here is the unit that I want. I want my answer to have grams in it. So I put myself in the best position possible by putting the gram unit right where I want it. The problem is the gram unit in this case came with moles. So what that tells me is now I know I need to cancel moles out. Don't cancel the grams out. So find something somewhere that we've talked about that can cancel out moles. The other thing I know is I need to cancel out moles. So that tells me automatically that the mole has to be up here. That way I can cancel that out with that because that's numerator denominator stuff. So, and I'm looking for molecules. So I could say 1 mole is equal to 6.02 times 10 to the 23rd molecules. Great. I got rid of my moles, but now I have this molecule thing. But that's okay because I was given molecules. I was given 1 times 10 to the 9th molecules. Oh God, this is going to be a really small number. So now molecules will cancel out. So 294.43 times 1E9 divided by 6.02E23. So this is 4.89 times 10 to the negative 13th grams. So like 48.9 picograms, like a ridiculously tiny amount. Because even though this is a billion, so we're saying we've got 1 billion aspartamines. A billion aspartamines, if I put that on your tongue, you wouldn't taste it. You wouldn't know it was there. You'd have no idea. I'd have no idea it was in my hand because a billion molecules is nothing. So are you asking me what 4.89 times 10 to the negative 13th grams means? Was that your question? No? Oh, I keep saying E. Oh, on a scientific calculator, the E key is equivalent to times 10 caret. So when I type in 1 point or 1 times 10 to the ninth, I type 1, I hit the E key, and then I type 9, and the calculator knows that that is that. It's just a quicker way to do scientific notation and a better way. And the calculator wants you to do it like that. If you type this into the calculator, sometimes you need parentheses to make sure you don't mess something up. But when you type it in like this, the calculator knows the 1, the E, and the 9 are tied together as a single unit or a single number. Yeah, I guess I'm just saying E out loud as I'm typing. I wonder if that would work in Desmos. I if it doesn't, they should change that immediately. But I have never used Desmos, but the math department loves it, and so there's no way they would love it as much as they do if that didn't work that way. So next time, just type an E in instead of times 10 caret whatever. It'll almost certainly immediately change it for you into times 10 to the what's the mass of one molecule of aspartame? Okay, again, that's a silly question, but fine. So I need to know mass, so I'm going to start with my mass number, like I should, 294.43 grams for 1 mole. And then I need to cancel out the mole, so 1 mole is equal to 6.02 times 10 to the 23rd. Molecules. What am I doing here? Oh, and then molecules. And I want to know about one molecule. So the molecule cancels out, and basically I'm just taking 294 and dividing it by a mole. Yeah, it's a ridiculously small number, so we'll just say 5 times 10 to the negative 22 grams. Uh, yeah, so a decimal place of 5 or a decimal place 21 zeros and a 5. So an incredibly small mass. It doesn't seem big. It seems really small. That's actually way worse. Why did I have it selected? Stroke eraser. Oh, I see. It deletes everything I typed the second it touches it. Interesting. Okay. All right. The number of atoms in a mole of helium. Okay. Well, how many atoms are in 1 mole of helium? No, that's not what you're asking me. It asks how many atoms there are. No, if you have 1 mole, you've got 6.02 times 10 to the 23rd. So if you have 3 moles, you'd have, what is that, 1.8 times 10 to the 24th? I just take a mole times 3. No. Is somebody else talking? No? Oh, you don't know. Let me see. No, Brittany isn't. I actually haven't heard Brittany's voice before, and her mic's muted. Brittany, can you try to talk? Or do you not have a mic? We're just trying to determine if this problem with mic being muted is the problem with me not being able to hear her is her problem or my problem. I'm guessing you don't have a mic because it says, well, it's just muted, and I tried to unmute you and it wouldn't. So that usually means, oh, no, you're there.
Can you hear me?
I can hear you, Bethany. Did you hear her, Brenda? All right, so it's you. I don't know what's wrong with your computer, Brenda, but your microphone's not working. Thank you, Bethany.
Mm-hmm.
Now you're muted. I'm going to force unmute you. No, still can't hear you. Yay, technology. Bethany, did you have any questions? You can either talk or type in chat like you usually do.
Are we doing chapter 4?
I'm just answering questions. Yeah, I don't know, Brenda. That doesn't make any sense. But oh wait, you know what? This happened to us before. This same thing happened when you Zoom with me during my tutoring time in the or in Hood River campus. It's like your microphone works for 10 minutes and it's like, nah, that's all I got. The video is way more intensive than the audio, so I'd assume your video would go down long before the audio would. I mean, it's thousands of times more bandwidth intensive than audio. I could grab the book and like skim 4, see if there's something you want to talk about. I don't actually know if we finished kind of talking about 3. Yeah, we were talking about 4 before. I'm positive because we were talking about the. Oh yeah, we definitely did. Some of the important things that we're looking at in 4. So if you have the text, go to page 173. The figure at the top is called a calorimeter or a bomb calorimeter. And it's an interesting apparatus that was developed for studying how much energy a particular substance has. So what you do is you've got this contraption that has 2 containers, and the container on the inside has something in it, and the container is placed in water in another container. So you can see there's an arrow there that's pointing to that light blue stuff. So the container with the stuff that you're going to explode, catch on fire, is going to heat that inside yellow container up, and then the water is going to heat up. So if I know how much energy the water absorbed because I can check what happened to its temperature, then I can know how much energy was given off by whatever it is that I caught on fire or ignited. This is how we figure out how many calories are in food. We literally stick like a peanut down there, know the exact mass of the peanut, ignite the peanut burns, it burns to ash, and the water temp heats up, and then we calculate the number of calories that food transferred to the water, and then we know how many calories it has if it was all turned into energy. I've got a huge issue with all nutrition in the United States because typically it's just terrible. And the information is terrible. And this idea of calories is, in fact, terrible. So let's stick with a peanut. Would either of you say that a peanut is a bad thing? Like, as long as you don't have a peanut allergy? Like, is that a bad food? No answers? It's not, right? I'm like, no one's going to be like, hey, you should watch your diet, stop eating those peanuts. Except when you look on the bag of peanuts, the value for the calories is large. It's actually a big number. So does that mean I should eat a smaller bag of potato chips that has less calories than eat my little baggie of roasted peanuts? The answer is no, because when you burn that peanut, you burn the carbohydrate in the peanut, the fat in the peanut, and the amino acid proteins in the peanut. So when you eat a peanut, the entire peanut doesn't get turned into energy. A small portion of it will get turned into energy. Most of it is going to be used to build things. And this calorimeter on 173 doesn't take that into account. This takes into account I am starving and my body will tear this peanut apart to use every bit of it to give me fuel. But that's not the case. People eat peanuts and your body tears that apart and uses the fats to build cells, uses the amino acids to build proteins. So those things were never burnt. So they don't contribute to your caloric intake. They contribute to your nutritional intake, which is a different metric nobody bothers to disseminate to the general public. I don't know if it's too complicated or whatnot, but the calorie thing is dumb. Okay, so we would use something like this to measure the amount of energy stored in anything. Like you could put some gasoline in there and know how much energy is stored in gasoline, or you could put a piece of coal in there and figure out how much energy is in the coal, or a piece of oak versus a piece of birch versus a piece of pine, and you can know which one of those pieces of wood, even though they make sure they're the same mass, are generating how much energy each of those are generating. So you'll know which one of those things is more efficient for you to throw into your fireplace. So there's lots of uses for this, but it's called heat of combustion, and we figure out how much energy it's given off, and we do a lot of calculations with that, and it's super useful for lots of things that we do. Something else that's important to understand would be if the reaction itself gives off energy or takes in energy. So giving off energy is exothermic and putting energy in is endothermic. So if you want to, let's say, we'll make it easy. If you want to burn some propane, you know that thing's going to be giving you energy. Otherwise, you wouldn't have hooked it up to your barbecue grill because you want it to produce heat. But you're not going to put carbon dioxide into the tank for your barbecue grill because carbon dioxide doesn't provide energy. To break carbon dioxide apart, you have to put energy into it. Most of the time, that's photosynthesis. So you wouldn't. That would be a poor choice as your fuel, since it would be an endothermic substance. The table the graph that's on 182 is useful and interesting. So if you look at the axes, the y-axis is energy, and the x-axis is basically just time, like how long the reactions happened. So it says reactants there, and it's sort of in the upper portion of the beginning of the graph. And so these reactants have a certain amount of energy. I know that because they're on the y-axis and it's kind of high up there. And the reaction starts, and to get the reaction going in the first place, you have to put in some energy. And the reason is because breaking a chemical bond takes energy. Even if the reaction itself ends up giving me heat, like my propane reaction, initially to break the propane molecule apart, you have to put energy into it. So I put energy into it, and in this case, this reaction is exothermic, and I know that because the products have a lot less energy than the reactants. And since energy isn't destroyed, it just gets transferred from place to place. That means that the reactants gave off, in this case, probably a bunch of heat and then turned into this product. So this would be considered an exothermic reaction. An endothermic reaction, the orientation of the reactants and the products are backwards. The reactants are at the bottom and the products are at the top. So photosynthesis would be an example of this thing being reversed, where cellular respiration, this is what cellular respiration looks like. And you know that because you don't need energy to undergo cellular respiration. If I put you in a closet and close the door and you're in total darkness, your cells still undergo cellular respiration. But if I put a plant inside of a closet and close the door, photosynthesis ceases to happen because they need a constant energy input for their process to occur. The kind of interesting other part is the fact that there's that bump, the reactants, and then it goes up before it comes back down. So you see that all the time. If you want to light a candle on fire, you put a match to the wick. So what is that match doing? That bump on that green line there after the reactants before the products, the match is adding that bump of energy. And what it's doing is it's allowing the fats in the candle to be broken apart and combusted. But that candle's wax, when it burns, it produces so much heat that then it can actually initiate the next chemical reaction, which is why you can put the match on, and then once it's lit, you can take the match away. So it's producing way more than enough energy to perpetuate its own reaction. So it's a positive feedback loop, and it keeps going until you run out of fuel. What's the best biofuel according to 4.2? 4.2. Even though E85 is significantly higher octane rating than even regular, the energy per gallon is less. Translates to fewer. Are you asking me why that's the case? Why the E85 has a doesn't give you as many miles per gallon? Bethany?
On chart 420,
Yes.
according to that chart, what's the best biofuel?
Oh, chart. Sorry, I'm looking at the wrong thing. What page is that?
That's page 182.
182. 182. I don't have a chart on 182.
That was the chart we were just looking at, the reactants. Energy.
This chart wouldn't help with that. So the best chart, every single chemical reactions chart is going to look a little bit like this, but the bump is going to be bigger or the bump is going to be smaller. The differentiation between the amount of energy from reactants to products is going to shift. All of these reactions have different things. So the one that you would want them for the best fuel, it would have the smallest bump, and it would have the largest differential of energy between the reactants and the products. And the product's energy would be much lower than the reactants. So whichever one does that. But as far as which one does, I can't tell you off the top of my head. The longer the molecule, the more energy dense it is. So if we're talking about like people with diesel motors using veggie fuel, so really long chained fats would provide more energy density.
They're using a corn picture, or they're trying to put a piece of corn.
Yeah, the reason they're doing that is because a significant portion of the corn in the United States isn't sold as food. It's fermented and turned into ethanol. And so then on the picture below that, it shows E10 and it shows E85. So that's 85% ethanol. And ethanol is actually drinking alcohol. But it's sort of a way to say it's a renewable resource, right? Because where did the ethanol come from? It came from corn. So if I'm a farmer and I can sell my corn as corn to humans, as corn to cattle, or turn it in, sell it to somebody who's going to turn it into ethanol, that just gives me more markets to sell my fuel. The problem with that is you're turning food into gas. So that means there's less food. And most of the people in the United States are fine, but the U.S. exports four things. Exports four things. They export entertainment. They export guns or weapons of some kind, and they export fuel. So those three things. Sorry, not fuel. Food. So if we export less food because we've turned some of that food into ethanol, then more people in the rest of the world are going to starve to death. Is really what it works out to be. There are other ways that we could be fueling things up, but this makes farmers happy, and that sounds great. Great. I want to make sure farmers are happy. The problem with this is these aren't regular farmers. These people don't farm. This isn't like a father and maybe the grandparents and 4 kids working the farm. This is an industrial field that's owned by a company. And they're getting lots of money to sell this stuff instead of selling it as food, selling it as fuel. And they get tax subsidies for doing it because we haven't built a very mindful tax code. So turning corn into ethanol is a bad idea. The good idea is to pull those corn kernels off and sell them as food, either to us or cattle or some other food, somebody else who wants to eat that, and then take the corn cobs and the husks and turn those into ethanol, which we can do. Farmers who sold corn for food and for feed used to have to pay somebody to take away those cobs, and now they get paid to sell those cobs to people who turn it into ethanol. That's what we should be turning into ethanol, byproduct stuff. I don't know if that answered your question.
Table 4.2, there's a lot of fuels that use carbon and hydrogen. Where would ethanol fit in there?
I'm so sorry. Which 4.5?
4.2, page 167.
167. Alrighty. It's not on this list, but it's very close to ethane, the second one on the list. If you take an oxygen and you put it in between, if you pick either one of those carbons, it doesn't matter, and then pick any of the hydrogens connected to that carbon, and if you insert one oxygen in between any one of those carbons and any one of those hydrogens, you've got ethanol. I could even, let's do it like this. Share screen to, and come over here. Let's see, Control A, delete, no, Control A, delete. What's going on? Well, let me select everything. Oh, there we go. So here is ethane, and ethane is one of the 3 gases that's found in natural gas. So if instead of doing ethane, I take out one of these hydrogens for just a moment, and I insert an oxygen and an H, this makes it ethanol. So you can drink that, and it'll inebriate you, and it won't kill you immediately. But it's the only one. Only one of the ethanols that won't kill you right off the bat. So like if you had this is rubbing alcohol. And if you drink like 2-3 ounces of this, this will kill you. Or or this one is called methanol. And if you drink a couple of ounces of this, that will kill you. It's just odd that the 2-carbon version can be detoxified by your liver, and all the rest of them turn into, they either can't be detoxified or they turn into worse things and then turn your liver off and kill you almost immediately. Like 2 or 3 ounces of methanol, 2 or 3 hours later, you'll be dead. And none of the fuels on here are on this table 4.2 are biofuels. These are all fuels that you would get from petroleum, from a barrel of crude oil. I mean, you could make these from other things, from biofuels, but it would be labor and energy intensive. And when we could do it, I mean, we could use like solar or something else to do it, but typically this just comes out of a barrel of crude oil. On the next page, it shows you an oil refinery, and then on the next page, it shows you how you take a barrel of crude oil and not disassemble it, but unmix it and pull out into its substituent molecules. So at the very top of that distillation tower, it says C1 through C4. And if you go back to the page, back one page to that 4.2, there's methane that's got 1 carbon, ethane that's got 2 carbons, propane that has 3 carbons, and butane that has 4 carbons. And so what it's saying is those 4 molecules will come out of the very, very top pipe. And any molecules that are 5 carbons to 12 carbons come out of the second from the top pipe. Brenda, for the next time, do you suggest that we read through everyone's discussion related to it wouldn't be terrible. I mean, all you're doing is being exposed to the questions that you could possibly see on the tests and people's answers. I like Quizlet. Quizlet's good. I don't know how you flashcard Quizlet on this one. I mean, honestly, if I were you, I would just go to the back of the text and try to answer these questions. And if you can't answer these questions, then ask me or post it or do both. I mean, that's really what I'm hoping that the questions that people ask on the forum are, that you've gone through the question, you've read through the text, and then you go to the back of the chapter and read the questions here. And as you're reading them, I'm hoping you're like, okay, I could answer that one. I could answer that one. And then when you come across I don't know how to answer that question, that should be the one that you post online. That way you get feedback. Anybody else? Anything else you want to talk about?
One more question on hydrogen.
Go for it.
Does that work along the same lines as all the carbon-based fuels?
No. Hydrogen is a magnificent fuel. And we should absolutely be using hydrogen in everything. It's definitely the way to go, but we're not doing it right now because there's a bunch of rich people making lots of money selling us gasoline. So, so if we had hydrogen, you can combust it with oxygen and you can make water. I mean, your byproduct would be water. BMW created a car that can run on lots of different fuels, and one of the fuels that it can run on is hydrogen. You can literally pump in liquid fuels into one tank in the car and gases in another tank. I'm not sure if you've heard of people using propane as a fuel source for their vehicles, but it's a modification that you can get done for a couple of $1,000s. And then when you go to the gas station, you have to pick the right gas station. And then you go in and they just fill up your tank with propane like they're filling up your barbecue grill. So you can't do that with regular cars and have it turned into hydrogen. There's 2 reasons that would be a bad idea. One, it would melt your engine components because hydrogen, the process of converting the hydrogen into water is too hot for your car to handle. So that's obviously a problem. But the bigger problem is, where are you going to get the hydrogen from? we have an infrastructure to get gasoline and diesel and a smaller infrastructure to get propane, but we don't have a hydrogen fuel infrastructure. Do you guys know why we have a propane distribution center? Like why gas stations sometimes have propane in them? Because I will tell you, before I was born in 1970, gasoline stations did not have propane available. It wasn't something you could purchase. Does anybody know what happened in the 70s to cause us to change that?
Fuel shortage.
There was an oil shortage. OPEC said, hey, you're not getting our gas anymore because you're doing stuff in the Middle East and we don't like it. So they cut off our supply of crude oil, and there were long lines. Like you'd get up at 3 o'clock in the morning, drive your car down to the gas station and park it, and hopefully you got a good spot in line, and hopefully it didn't run out of gas in the morning before you got your spot. So Jimmy Carter said, you know what, we don't want to be dependent upon everybody, and the United States has a lot of natural gas, and cars that are built today can be converted to run on propane. So there was a federal program to make sure that if you were in San Diego, you could drive to Maine and hit gasoline stations along the way that would sell you propane for your car. And then Ronald Reagan took office, and all of that went out the window because he was a Republican with a bunch of gas people giving him money, and so they didn't want anything to do with propane. They just wanted to keep doing what they were doing because they were making money. So this process of using hydrogen in your car, I mean, we can do it. We can retool vehicles to use hydrogen as their internal combustion. So where are we going to get the hydrogen from?
Well, California has the hydrogen highway.
They do. They're in California is a special circumstance because they are so environmentally friendly. I mean, the whole reason your car has a catalytic converter on it is because of the state of California. And if they weren't as ginormous of an economic power, they wouldn't be able to do it. It's not like if Oregon said, hey, all cars stored in Oregon are going to have catalytic converters on it. GM would have said, we don't sell enough cars in Oregon to bother with you. But when California said it, they are right now the 7th largest economy on the planet. There are only 5 other countries that have a bigger economy than California. So obviously, the United States is one. And those 5 other foreign countries are the only ones that can compete with California. So when California said, you're not allowed to sell a car in California unless it has a catalytic converter on there, all the major automakers said, okay, we'll put a catalytic converter on there. And so California said, what we want is an infrastructure for hydrogen, for cars who can run on hydrogen. And so they did what Carter did across the country, except it's just in California. And there are fuel stations that will give you hydrogen. So most of the cars that are using hydrogen right now run on a different premise than an internal combustion. They work on a membrane and they produce electricity. It's sort of like a battery that is powered by gases, and the gas is hydrogen and oxygen. And so you still output water. What comes out of the tailpipe of those cars is water, except they literally don't have an internal combustion motor. Basically it looks like a sophisticated battery, but it looks weird. It doesn't really matter. Instead of using internal combustion, they use a membrane, and it's a fuel cell. And so the issue is we don't have enough of this hydrogen distributed across the country, and we don't have enough vehicles that handle this. So right now we're pretty much playing with batteries, right? Tesla's big, Rivian's coming online, Nissan Leaf, who else is out there? The Chevy Volt and the Chevy Bolt, and obviously the Prius cars. There's an all-electric Prius now. But that's a different process. You plug that thing in. The really cool thing about hydrogen, if you were to just use a membrane for a fuel cell or use it as internal combustion, the problem with electric vehicles is they take a long time to recharge. This would literally be you just filling it up. It would just be a different fuel you were putting in. So it'd take you 5 to 10 minutes to fill your car up, and then you have a full tank of gas and you're on your way. So the question is, where does this come from? how do I get hydrogen? Like, it's the most abundant element in the universe, most abundant atom in the universe, but it's chemically reactive, so most of it's combined with stuff. But we have a whole bunch of water on the planet, and if we run electricity through water, we get hydrogen gas. So where would we get this electricity from? Probably solar. So if we had solar panels run electricity through liquid water, we could capture the hydrogen gas, and then that could be our infrastructure. I mean, we can do it. It's super easy. It's not happening because there are people making money doing petroleum, and that's pretty much what we're stuck with. So I don't know. Maybe this 2020 election will change things. We'll see. But I like what you're thinking. That would be the best thing for all of us. Forget about batteries. Just run everything off of hydrogen, because then what comes out of your tailpipe is water.
It's also slow to get hydrogen out of them, though, right?
Slow to get hydrogen out? What do you mean?
The amount of electricity you get out of a solar panel is slow to get to take the oxygen out and to get the hydrogen.
That's just an engineering issue. That's not a big deal. You can wire up many solar panels to be in series with each other and get a larger voltage to make that all happen faster. I mean, there are people around the country that already do this. They literally just use tap water, and they've got a drying system for the hydrogen that they produce, and they run everything off solar, and they're completely off grid. They power their house with it, heat, electricity, everything. It's totally doable. And it would be super cheap because solar panels are now a lot cheaper than the amount of energy you get out of coal, and we don't wreck the planet. I mean, Elon Musk again is talking about his Arizona idea where he covers 1/4 of Arizona in solar panels and powers the entire United States.
Okay, that was all my questions. Thanks.
Yeah, I don't know if Arizona would be your best choice. I think the best thing to do would be to build a barge, just pontoons, and put it kind of offshore, off the coast far enough to get it away from the continental shelf, and then just run electricity like that. You could have basically a giant barge of hydrogen of solar panels running across the equator with power lines coming off of it. The engineering isn't difficult to do that, and it would cost a bunch of initial cash, and then the rest of it would be very, very small amounts of money. Okay, looks like we lost Brenda. Do you guys have any more questions? Okay, great. Thanks for logging in and asking really good questions. I love your questions and your mindset. I will talk to you guys later. Have a good night.